So here we have another final exam. Nice. And this isn't just any final exam. Calculus 2. Locally we call this Math 166. We've got our techniques, we've got our applications, we've got our sequences and series. Lots of cool stuff to talk about and 8 problems to do. So wonderful things ahead. Of course, as always, if we want the credit, we got to make sure to put our name. So let's go ahead and start by putting our name. And we're ready to begin. Number 1, we want to find the volume of a solid formed by revolving the region in the first quadrant, bounded by f of x equals x squared and g of x equals a half x squared plus 2 around the y-axis. Okay, cool. Well, we know it's volume of revolution because we see words, right? We see lots of words, but the words that we see, volume and revolving, that tells us volume of revolution. See, we learn to pick up on cues, because picking up on cues helps us know what to do. And it's a lot easier to do a problem when you know what to do. 4 out of 5 dentists recommend that. Now, in order for us to make progress, we need to get some intuition about what's going on. So, we're in the first quadrant, and we have some curves. Now, x squared, classic, parabola. We know what that looks like. A half x squared plus 2, well, the plus 2 vertical shift, then the half is putting it down. So it's going to come up here to 2, and it's going to look similar, but a little more squashed. And so we have this very nice shape, and we'll go ahead and shade it in for right now. Okay, so there's our shape. Now, one of the things we're going to need to do at some point, we'll do it right now, is where does that intersection occur? To find it, you set the curves equal. So, okay, one does x squared equal a half x squared plus 2, or one does a half x squared equal 2, or x squared equals 4. Well, in the first quadrant, that happens at 2. Okay, now there's something very important that we haven't marked yet. We know we're doing a volume of revolution. It's super duper important. And notice it's not just super, it's super duper. Super duper important to make sure we know how we're revolving, or if you like, what we're revolving around. So we are around the y-axis. So we mark that, because depending upon how you revolve and what you revolve around, your approach changes. So what do we do? What's our technique? Now, what I would say is we have these curves given to us in terms of x functions. And so, for instance, this bottom curve, that's x squared. And this top curve, that's a half x squared plus 2. So since we're thinking in terms of x, let's integrate with respect to x. So that says when we slice, if we're integrating with respect to x, we're going to have vertical slicing. So we're doing small little slices. So when we spin, what shape gets formed? And that determines the technique we use. So we spin it and spin it to win it, right? What do you see coming out? What's the shape? Cylinder. Okay, so we say great. So we're going to do shell method. And shell is short for cylindrical shells. Cool, 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 cool. Okay, now we know the right technique. We have to dig through our memory, say what's the right formula? Well, for that, I like to say, remember how things break apart. So I don't try to say, oh, it's fx, g of x, blah, 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 blah. That's hard for me to remember that. So I say, look, everything in integration is about adding up. So we're adding up our pieces. You say, well, what's the volume of a little piece? Well, for shell method, you have 2 pi, a radius, a height, and a thickness. Now, the thickness is this little change. We're going to with respect to x, so in our case, dx. Height. Height is this part. So in our case, it's between the two curves. So how do you find height? Top minus bottom. All right, well, so for us, height, top minus bottom, which is the top curve, 1/2 x squared plus 2, bottom curve, x squared. Radius, what's that? Well, radius is this length. It's how far from your slice to where you spin. All right, well, how do we find that? And how do we find it in terms of x? The answer is, it's x. The distance to the y-axis is x, not y, x. So that's actually pretty simple. That's cool. Now what about the 2 pi? Oh, cool answer. It's still 2 pi. It's a number. Where do you start and where do you stop? Well, where does the region start? Where does the region stop? From 0 to 2. Okay, so let's write this down. So we have the integral 0 to 2, 2 pi x, and when we do the subtraction here, that's 2 minus 1/2 x squared dx. Well, 2 pi, of course, you can pull out. Oftentimes people write it on the outside to begin with. The x you can distribute. It's a polynomial. Polynomials are nice. Don't have to do any fancy techniques. Not yet. We will, but not yet. We say, okay, what do we get? Well, we get 2 pi, integral of 2x, x squared, integral of x cubed, x to the 4th over 4. So there's already an over 2, so 1/2, 1/4, 1/8. And evaluate 0 to 2. Nice thing is, plug in 0, you get 0. So we just have to plug in 2. So 2 pi. Now that won't always be the case. So double check, be careful. They're really good, by the way, at knowing how you think, because they programmed you. So you got to be really good at saying, I'm not going to let you try to get past my tendencies. I'm always going to check the process. All right, anyways, back to our regularly scheduled problem. 2 squared, 4. 2 to the 4th, 2, 4, 8, 16. Divided by 8 is 2. 4 minus 2 is 2 times 2 pi. 4 pi. Ah, good. A positive number. If we'd got a negative number, uh-oh. Now, if we got a negative number, we'd fix it. Probably a negative would come from this part right here. But it's good to double check the whole thing. But now, that seems pretty reasonable. And we're one problem down. Woohoo! Yay! Let's keep going. Number 2. Find the center of mass of a thin plate of constant density covering the region bounded by the parabola y equals x squared and the line y equals 4. See the diagram. So in particular here, let's go ahead and shade this in. We have our thin plate. Sometimes they'll use a fancy word, lamina, but I don't think they want it to be fancy here. So there we go. There's our thin plate. Constant density. That's good. It simplifies things. So one of the things it does is it says, hey, if you have constant density, look for symmetry. Do we see any symmetry? And we do. We see symmetry right here. So this is a line of symmetry, which tells us what? Well, it tells us automatically our center of mass has to be on that line. So we can say that tells us x bar equals 0. So even if we got nothing else right, by pulling out symmetry, and saying, hey, that tells us x bar equals 0, we'd get some credit. And we want all the credit, right? So it's good to get that low-hanging fruit, right? Get that low-hanging fruit. All right. Well, now we have to say, great, but where? Where? And, you know, eyeballing it, it probably should be somewhere up here. So we're going to check at the end. Is it somewhere up here? Now, why do I think up here? Well, there's more mass at the top than there is at the bottom. So we should be biased to that side. All right, so what do we need? Well, we can say that our y bar is m sub x over m. Now, remember, what is m sub x? This is the moment with respect to x-axis, and we'll talk about what that means, and m is the mass. What's really going on here is y bar is the average y value. That's what's going on. Okay, so let's talk about how we figure these out. Well, mass is pretty simple. So we'll do mass first. Start with the things which are easy. It's no problem. Mass, you add up, and then it's density times area. That's it. That's mass. See, density is how much mass per area. So mass per area times area is the mass. So this is the mass of a little piece. So then you add them up. Now, there's some subtlety here. What's the subtlety? So let's talk about it. We are going from -2 to +2. Our density is constant. They didn't tell us what it is. Since it's constant, let's go ahead and assume it's 1. Cool. So then it's our area. Now, how do we find our area? Well, think about, we're chopping it into little rectangles. We're integrating with respect to x. So it's height, top minus bottom, times width. Height times width. So that's area times density. So we get 4x minus 1/3 x cubed, because that's the integral. And we evaluate from -2 to +2, which will give us 4 times 2 is 8, minus 8/3. Subtract -8, and then plus 8/3. You can save yourself a little bit of work. Say, well, by symmetry, I just integrate from 0 to 2 and double. Be careful, though. We'll talk about how to be careful in a second. Okay, so this is the same as 16, 8 plus 8. Subtract 16 over 3. 48 over 3. Subtract 16 over 3 gives us 32 over 3. Now, this is not our answer. That's just the part that goes there, which is good, because that's like 10. That would say our center mass is off the screen, which would be wrong. All right, so there's our m. We'll need that later. Now we'll go to moment. Okay, so how do you find moment? Well, the moment is very similar. You add up. The only thing that happens is you have your density, and you add a distance and an area, right? So there, you add this piece, distance. So for us, say, look, we still have -2 to 2. What's our density? Well, still 1. The thing is, it doesn't matter which density you pick, because you're taking a ratio. The constants cancel. So you're fine with whatever number you picked. Okay, cool. We'll come back to distance. The area is still 4 minus x squared dx. Now, how do you do distance? Well, it's distance to the x-axis. So think of this rectangle. where's the center of mass? It's right in the middle of it, right there. So what's that distance? Well, where is that point? It's at the x-coordinate is x, and then the y-coordinate is halfway between. So it's 1/2 of, and then you would add. So it's like you're averaging 4 plus x squared. So the distance is 1/2 4 plus x squared. Okay. So distance, density, area. Now, if you remember formulas, which is because you're really smart and you're not old like me, you probably say, oh yeah, it's 1/2. And what happens here is you distribute these and you say, oh, that's 4 squared minus x squared squared. And that's if you're really good at remembering formulas. I'm not, so I just go through the process. But if you are, that's cool. You're awesome. I like you. All right, well, let's go ahead and work this out. So -2 to +2, and 1/2, you'll have 16 minus x to the 4th. Now notice these are both even functions. So we didn't take advantage of it here, but let's take advantage of it now. So this is the same as double the integral from 0 to 2. So there's double, because I'm only doing half of it. There's 1/2 from that half, and then there's 16 minus x to the 4th. Well, the nice thing is 2 times 1/2 is 1. And what do we get? Well, we integrate, we get 16x minus 1/5 x to the 5th. Evaluate 0 to 2. Well, 0 is easy to plug in. We get 0. So what do we end up with? Well, we end up with 32, 16 times 2, minus 32 over 5. Now, if you multiply that, well, you can pull a 32 out, right? So this is really 32, 1 minus 4, sorry, 1 minus 1/5, which is 32 times 4/5, which is 128 over 5. I have to leave myself a little bit of room to finish the problem. Okay, so where are we at? We started really quickly, we found x bar. We say there's a way to find y bar. We found the pieces for y bar, so we need to compute. So we have y bar is mx over m, which is 128 fifths. That's our mx. And then over m is 32 thirds. Now, because it's over m, I'm going to flip. See that? It's multiplied by the reciprocal, 3 over 32. Now, it turns out 32 goes into 128, and that goes in 4. So 4 times 3 over 5, also known as 12 fifths, or 2.4. So let's go back to our picture. 2.4 puts it about here. Does that feel about right? Well, yes, it feels good, right? If we'd been above 4, trouble. We know there's a little bit more mass on top than there's on the bottom, so we should be a little bit above the middle. So the middle is 2. So 2.4 says, yeah, you drift up a bit. So it matches our intuition. So this is a very reasonable answer. It's also because it's correct. But sometimes it's hard to tell if it's correct, but it's usually not hard to tell if it's unreasonable. So check, check. So putting it together, we get that our center of mass is at 0, 12 fifths. Whew! Wow. Good work on that one. But we made it. Good for us. Let's keep going. Number 3. Find the length of the polar curve r of theta equals 2 theta squared. And theta goes 0 to 2. Now, it turns out length is interesting because we do it 3 times. So what are our 3 cases? Well, one case is y equals f of x. And in that case, what we do, integrate a to b, the square root 1 plus f prime of x squared dx. Another case is parametric xt, yt, and in that case, a to b, square root x prime squared plus y prime squared dt. The third case, which is the one we're going to do, is r equals f of theta. And in this case, well, alpha, beta, and the square root of, it's the function squared plus the derivative of the function squared, d theta. So those are the three ways we can encounter length. Now, if you're only going to memorize one, memorize the one in the middle. That's the one that gives you the other two. So how do you go from parametric to polar? Well, you say x equals f of theta cosine theta, y equals f of theta sine theta. You do half a page of computations, and it comes out to that. So ideally, you'll just have this memorized. You're young. I believe in you. You've got some spare neurons. You can do this. So, okay. So now we say, great. We know the formula. What comes next? Well, what comes next is we apply it. So we know our bounds, 0 to 2. Square root the function for, oh, I'm squaring it for, okay, let me do it slowly. 2 theta squared, right, because I was squaring that. The derivative of that. So the derivative of 2 theta is 4 theta. So plus 4 theta squared d theta. Okay, so that's integral 0 to 2 square root. Well, we have 4 theta to the 4th plus 16 theta squared. All right, what can we do? Well, we can pull stuff out. Let's pull out, notice that we can factor 4 theta squared out. So 4 theta squared times theta squared plus 4. And if we do that, well, we can take the square root of 4 theta squared. Because theta is greater than or equal to 0, we don't end up with absolute values, which is good. So 2 theta square root theta squared plus 4. Now at this point you're like, oh, partial. Oh no, we're going to do like some crazy things. I almost said partial fractions, but no. It's like, trig substitution. No, we're not doing that. What are we doing? We're going to be smart and say, look, before we try trig substitution, try substitution. In other words, try simple techniques before we try complicated techniques. And notice, if you take the derivative of theta squared plus 4, what do you have? 2 theta d theta. It's almost like they planned it, because I think they did. Your teachers, they love stuff like this, where things work out nicely. So, it won't happen 100% of the time, but you should look for nice things to happen, because it will happen somewhere on the test. All right, that's 2 theta d theta. Cool. So we now have integral 2 theta d theta becomes du. The square root of theta squared plus 4 becomes square root of u. Calculus-friendly way to write that, u to the half. Update the bounds. These are theta bounds. We want u bounds. So if we have theta is 0, u is 4. If we have theta is 2, u is 8. Okay, cool. Now, what comes next? Well, we're surprisingly close, right? Because they're like, it feels like Calc 1 from here, because it is. So we add 1 to the exponent, get u to the 3/2. Don't forget that 2/3. And we're going to go u equals 4 to u equals 8. We don't have to go back to theta. The nice thing about when we have definite integrals is it's always forward looking. We never have to go back. All right, so that gives us 2/3, 8 to the 3/2, subtract 4 to the 3/2. Well, how do we handle that? Well, from here it's just simplifying, so we'll be a little careful. Now 4 to the 3/2, we can do 4 cubed, which is 64, and the square root of 64 is 8. That's not how we really do it. This is really 4 to the 1/2 cubed. 2 cubed is 8, so that's an 8. How about 8 to the 3/2? Well, 8 to the 3/2 is the same as 8 to the 1 times 8 to the 1/2. It's a true story. Exponents add to 3/2. And 8 to the 1/2, well, what can we do? One thing we can do is we can say 8 to the 1/2 is like 4 to the 1/2 times 2 to the 1/2. So that becomes 2 times square root of 2. And then we have this part here, minus 8. So pull out an 8, we end up with 16 over 3, 2 root 2 minus 1. Now you're probably thinking, wait, couldn't I have stopped here? Yes. Why? Because it didn't say to simplify. And so once you got to a number, you say, look, there's my number. That's my number. I like my number. I'm sticking with this number. But if you want to, you can go a little bit further. Both are good. All right. Whew. Let's keep going. Number 4. We're asked to find the integral of x squared cosine x. Okay. So, first thing is, do we recognize this type of problem? Well, we have something that, it's not on our formula sheet, but we say it has 2 parts multiplying together. And with cosine, whether you integrate or differentiate, doesn't really do much. X squared is the messy thing. We'd really like to get rid of it. We say, hey, if you take a derivative, it becomes simple. If you take 2 derivatives, it becomes a constant. And that's basically, it's gone. So this is a classic integration by parts. All right. So we're just going to say, okay, let's work through our integration by parts. So let's start by writing down our formula. So this comes from our product rule. So the integral of u dv is uv minus integral v du. And you have to sort of go in with a plan. Which part is differentiated? Which part is integrated? Sometimes there's a little bit of flexibility. Sometimes there's not. If there's something you can't integrate, that's the part you have to differentiate. Otherwise, if there's a polynomial, that's the part you should target. Because when you take derivatives of polynomials, they start to disappear. And so that's our mindset. So we say, okay, so when we're thinking of u dv, the u, that's the part we're going to differentiate. The dv is the part we're going to integrate. So du would be 2x dx. The integral of cosine, ooh, be careful, positive sign. Yeah, you have to be careful because sine and cosine are really tricky that way. You have to remember, where does the minus come in? So we now have, if we do integration by parts, x squared cosine of x dx is u times v. So that's x squared sine x uv minus integral of v du. So I'll put the 2x in front, sine of x dx. And now we're like, okay, so instead of having to integrate x squared cosine x, we can consider the problem of 2x sine x. And you're like, it sounds like a similar problem. It is, but it's a similar problem. Instead of x squared, it's just x. And so now you say, well, what do we do? Well, it's a technique so nice, we'll do it twice. So we've already committed with our u's and dv's. So we don't want to switch. If we switch, it undoes all the good we've done. So the polynomial part is still u. The trig part is still dv. du will be 2 dx. And then the integral of sine is negative cosine. Yeah, that's why I said be careful. And so, what do we have? Well, we copy from above. X squared sine of x. That just follows along. Don't forget it. Minus, I will tell you, a lot of people lose points right here. Parenthesis. So we want to put stuff on the inside. Okay, so uv minus 2x cosine x, right? There's our uv, minus the integral v du, which is minus 2 cosine x dx. All right, now let's unravel these minus signs, because there's a lot of them here. And what do we get? We get x squared sine x. Minus minus makes a plus 2x cosine x. Minus 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 leaves us with a minus 2 integral cosine x. All right. And look, one of the ones that we know by heart, a beautiful integral, x squared sine of x plus 2x cosine of x. And here we're going to get the integral of cosine is sine. We still have a minus 2, so minus 2 sine of x. And don't forget plus c, because it's an indefinite integral. And there we go. Wow. Nice. So it's just a matter of recognizing the tool we need, remembering the tool, and working through it. This is an onion problem because it has layers. And like onion problems, some tears may be involved, but that's all right. We'll get through it. Cool. Let's keep going. Number 5. Using integration, find the area, A, of the region in the first quadrant that is enclosed by the x-axis, the y-axis, and the curve y equals square root of 9 minus x squared over 3. So it's this diagram here. Now, if this shape looks familiar, you can think of it in a couple of ways. One is it's part of an ellipse, because it is. Another way is to think of it as you start with a circle of radius 3 in the first quadrant, and then whoop, squashed it. And so there's ways to do that geometrically, but we're going to follow the instructions. What are the instructions? Use integration. Okay, so we got to use integration. So we say, all right, well, area, that's one of the first things we learned with integrals. Area is the integral a to b, well, in our case, 0 to 3. You can even count 1, 2, 3. And you can see 9 minus 9 is 0. So, yeah, 0 to 3 of the height, 1/3, 9 minus x squared to the 1/2 dx. I write it as 9 minus x squared to the 1/2 because that's the calculus-friendly way to write this. And we're doing calculus, so we should be friendly. Okay, well, what can we do? At this point, we have to do trig substitution. There's not a nice way to proceed otherwise. Unless, of course, you wanted to think geometrically, but again, it says use integration, not geometry. And so we can't use geometrical arguments. If we could, we'd already have been done. All right, so what's this trig substitution? So let's review that really quickly. If we have a squared minus x squared, which is what we do right now, then x is a sine theta. A squared plus x squared, tangent theta. And then x squared minus a squared, secant theta. So those are our trig subs, and we make sure we know them, and we make sure we know which setting we're in. So we're in the 3 squared minus x squared. So we say, we're going to let x equal 3 sine theta. Now, by the way, you might say, could I have chosen x equals 3 cosine theta? Yes, but we go with sine. Why? Because we like the song. I saw the sign and opened up my eyes. I saw the sign. So that's why we're going with it. Well, that's not the only reason, but that's why I like to do it. The real reason is when we come to dx, the derivative of sine is positive cosine. And then the more we can avoid minus signs, the better. So here we go. So our updating integral. Now, x is 0. For what value of theta does 3 times sine theta equal 0? Another way to say this is, when does sine of what give 0? Sine of 0 gives 0. Cool. So this is theta equals 0. And these are just to emphasize what we're doing right now. Changing the bounds. Okay, what about 3? X equals 3. 3 equals 3 sine theta. Sine theta equals 1. When does sine theta equal 1? At pi halves. Okay, so 0 to pi halves. Then we have a 1/3 coming from here. 9 minus x squared to the 1/2. Well, let's do that on the side. We'll switch colors. After all, I've been using the same color now for 15 seconds. I better switch. Otherwise, disaster might follow us. So 9 minus 3 sine theta squared to the 1/2. So this is 9 minus 9 sine squared theta to the 1/2. Well, that's 9. 1 minus sine squared theta to the 1/2. Or 9 and 1 minus sine squared is cosine squared. That's the whole reason we're doing trig sub, is so we can do this step. So essentially the goal is to say, we'd really like this to be a square. And trig says, I've got a great bargain for you. I can help with that. So what ends up happening, we'll get square root of 9 is 3. Square root of cosine squared is cosine. Now you might say, oh, do we have to do absolute values? No, because we're going from 0 to pi halves. And in that range, cosine is positive. So, back to our problem. So we've updated our bounds. Good. We copied our 1/3. 9 minus x squared to the 1/2, we just figured that out, is 3 cosine theta. Dx is 3 cosine theta. All right, 1/3 times 3 times 3 puts a 3 out in front. And we have cosine squared. How do we integrate cosine squared? We do power reduction. So cosine squared is the same as 1/2 1 plus cosine 2 theta. It's one of those 6 trig identities that you should know by heart. So cosine squared, sine squared, know them both. So, okay, cool. And, well, so that's 3/2. Now we can integrate. Integral of 1, d theta. Theta. Integral of cosine is positive sine, so that's good. but account for the 2. So you have to divide by a half. And then evaluate 0 to pi over 2. All right. I'm going to make a comment in a second about this half. So I'm coming back to it. Don't forget. If I forget it, you say, Steve, don't forget. You said you're going to make a comment. And I'm like, oh, yeah. Plug in pi halves. Well, pi halves is pi halves. Sine of pi, 2 times pi halves, sine of 0. Sorry, sine of pi is 0. So we end up with 3 halves times pi halves. That's 3 pi over 4. Plug in 0, you get 0 and 0. Oh. So we're done. 3 pi fourths. Nice. Okay. Cool. Now, what was my comment? If you had forgotten the 1/2 here, put theta plus sine 2 theta, you still would have gotten the right answer. Would you have gotten all the points? No. We're very particular. Even if it's a mistake, that doesn't change the final answer. It's still a mistake. So be extra careful at every single stage. Look for the small things. The small things matter a lot. Okay, cool. By the way, could we have done this geometrically? Yes, there are geometrical ways to do this. So one thing is the area of an ellipse is pi AB, where A and B are your axes. So in our case, A is 1, B is 3. So a full ellipse would give you 3 pi. We don't have a full ellipse. We have a quarter of it. So that would be 1/4 of 3 pi, 3 pi fourths. We could have also come and said, hey, wait a second, pull out a 1/3. We recognize this geometrically. That's a quarter circle. And we know how to find the area of a quarter circle, and we would have gotten the answer. But those would not have been given credit because we wouldn't really be using integration. We'd be using geometry. So make sure to follow instructions. So there we go. 5 down. Let's keep going. Number 6. Using limits, find the value of the following improper integral or show that it diverges. Okay, so first off we have to say, why is it improper? So we have to worry about 2 things. 1, does it blow up anywhere that we care about? And 2, do we go off to infinity? Well, we definitely have a go off to infinity part. And so we have a plus infinity. We now go to minus infinity, so that's good. The other thing, of course, is I said, do we blow up? Well, we have stuff downstairs. Now we're going to make a quick note. So this is going to be 0 at x equals what value? -1. Are we worried about that point? And why not? Well, we're not worried. Good. Why not? Well, notice where we're going from. This is outside the interval from 3 to infinity. So it doesn't matter that it's blowing up. It's blowing up way over there. We can't even see it. It's so far over there. So we're like, great, no problems. So we only have one place to worry about. So we say, all right. So our improper integral, and we're going to use limits because, of course, we want points. We say our integral, 3 to infinity, 1 over x plus 1 to the 3 halves dx. Well, the only place we worry about is the bound. So limit as b goes to infinity, integral 3 to b. In the meantime, let's rewrite this to be calculus friendly. X plus 1 to the minus 3 halves power. Okay, we like it to the something to the power. Now, can we integrate that? Yes. That's a pretty straightforward integral. We add 1, so that's x plus 1 to the minus a half, then divide by minus a half, which is the same as multiply by -2. evaluate that, 3 to b. Well, okay, so that's the limit as b goes to infinity of, plug in b, that's minus 2 over, and we put over because of the negative upstairs, square root b plus 1, subtract, then we're going to have a minus 2 over square root 3 plus 1. Now, the good news is, for limits, there's only one thing we have to look at, which is down here. It's the only place b shows up. So what happens? Well, we see that this is getting big, the denominator is getting big, so that means negative 2 over big, this goes to 0, and now we're left with this part. Well, here you see square root of 4, which is 2. So this is square root of 4, which is 2. The 2's cancel, the minuses cancel, so we're left with 0 plus 1, which is 1. And there we go. Nice. So it's not too bad a problem. What are they check for? To make sure you actually used limits correctly, to make sure you identified the problems. And in this case, you were okay because there was only one problem. Sometimes there's multiple problems. So you have to be careful and walk that fine line. But that finishes number 6. Woo! We're making progress! Good for us! On to the next problem. Number 7. Justifying each step, determine the convergence of each of the following series. So let's start with A. So we have our sum from 2 to infinity for negative 1 to the n over n log n. Now, we see the negative 1 to the n, and so we say, it's plus minus plus minus plus minus. What happens to this n log n? By the way, the 4 doesn't do anything. The 4 you can pull outside of the sum. So we say, okay, we alternate n log n goes to infinity, and so 4 over n log n goes to 0. Now what does that tell us? If we alternate and the terms go to 0, then the punchline is, by alternating series test, this converges. All right, cool. Now, that wasn't so bad. However, there's some things that they might be particular about. I don't think they would actually force you to say, does it decrease monotonically, unless they were really, really being super particular. There's a little bit of a question, though, about what they mean by convergence. So, oftentimes when you use alternating series test, you might have something which is conditionally convergent. And so does convergence mean just converge, diverge, or does it mean absolutely convergent, conditionally convergent, divergent? And it's ambiguous here. So I'm going to hedge my bets just in case. Hopefully they won't make it ambiguous on the test. But if you're not sure, ask. It's the power of, saying, do you mean conditional versus absolute, or just converge? That simple of a question. And then you don't have to spend 10 minutes like, should I, shouldn't I? Okay, so back to the problem. So let's suppose we wanted to test conditional versus absolute. Well, let's look at this sum. N equals 2 to infinity, 4 over n log n. Now, here's the thing. What can we say about this? Well, one thing we can say is log n is going to be bigger than 1, at least starting at 3. So we'll start from 3. And because 2 does not determine whether you converge or not. So we say, oh, okay. Actually, no, that's not going to help us, is it? I was thinking of doing a comparison test. Comparison test won't work here. What will work? Integral test. In some sense, this is ideally suited for integral test. So compare it versus the integral of 4 over x log x from 2 to infinity. And what happens is you say, okay, u equals log x, du is 1 over x dx, and this would become the integral from log 2 to infinity of 1 over u du, which is log of u from log 2 to infinity, which is infinite. So this integral diverges. So this sum diverges. This sum is like super close to converging, like super duper close. It's ridiculous how close it is to converging, but it diverges. So by integral test, this sum diverges. And since we know when we have the plus minus, it converges. So we can say combining, this is conditionally convergent. Now again, this problem may not have wanted us to find whether it was conditionally versus absolute, but we did just in case. If you're on a test and you're not sure, ask. Please ask. Because if we didn't write the test well, we know what we meant, but sometimes we don't always write it that way. So please, please, please. Okay, part B. What's the sum? N equals 1 to infinity. Well, not what's the sum. Is it convergent? Absolutely. Well, it can't be conditional. Why can't it be conditional? There's no plus minus signs. Everything is coming up positive. So we are either divergent or absolutely convergent. That's our only two options. And we know, the instant we see this, we're like, I know what test we're using. What did we see? What did we see that tells us which test we're using? Which test is it? We saw the factorial. So when you see factorial, you say, aha, that's ratio test. Always going to be ratio test. So we know factorial is there, so we say, okay, so this we'll call our a sub n. And now we want to look at rho, which is the limit as n goes to infinity, a n plus 1 over a n. Because these are positive, I'm not going to put absolute values. Normally you put absolute values. Now, what's the punchline? If rho is less than 1, you're going to be absolutely convergent. If rho is greater than 1, you're going to diverge. And if rho equals 1, uh-oh. So, let's not get 1. Okay, so here we go. What do we have? So we're going to come through here, and everywhere where we see an n, we're going to put n plus 1. So we're going to be very careful here. So we're going to have 2 times n plus 1 factorial over 3 to n plus 1 times n plus 1 factorial squared. Okay, that's our an plus 1. Times that by an. Well, just flip it over. So that's 3 to 2n, n factorial squared, 2n factorial. All right. So, quick note. This part is 2n plus 2. So it's like 2n plus 2 factorial. Here, This is like 3 to the 2n plus 2. Cool. And yeah, that's my notes I need. So why do we like the ratio test? Well, because we have these factorials. The way factorials work is you can pull terms off. So because I see a 2n factorial, here I have a 2n plus 2 factorial. What we'll do is we'll start pulling terms off of the 2n plus 2 factorial. So that's 2n plus 2 times 2n plus 1. And then the next term would be 2n. We say, well, great. Stop pulling off, and then everything else all the way down. We also have our 3 to the 2n and our n factorial squared. Okay, that's from this part. Downstairs, well, this is 3 to the 2n times 3 squared. N plus 1 factorial is n plus 1 times n factorial squared. Right? We just pulled off, in this case, one term. And then we still have our 2n factorial. Okay, well, cancel. Nice. N factorial squared cancels. 3 to 2n cancels. And this is why the ratio test works with factorials. Lots of cancellations. The factorials will cancel out. Yeah. Okay. Well, what's left? Well, we have limit n goes to infinity, 2n plus 2, 2n plus 1, downstairs, 9, n plus 1 squared. Well, I'll do it a little bit slowly here. If you multiply this out, this would become 4n squared. And then we have a plus 6n plus 2. And downstairs, 9n squared plus 18n plus 9. How do you find this limit? Well, when you have polynomial over polynomial, if the degrees mismatch, if it's a higher degree downstairs, it goes to 0. Higher degrees upstairs, blows up. Same degree, look at the leading coefficients. It's the same idea as when we're doing our comparison test, limit comparison. Get rid of the noise. The thing which determines it are the leading terms. And what do we see? 4/9. Okay, so we get 4/9. What do we know about 4 over 9? We know it's less than 1. So wait, what does that tell us? It tells us absolutely convergent. Or just convergent if that's all it's after. All right, so great. It turns out they both converge. Top one is conditionally convergent, and the bottom one is absolutely convergent. Nice. Number 8, our final problem. Woo! Oh my gosh. It's been a long journey in Calculus 2, and it's nice to get to the end. So, we have 3 parts, but they're all related. So let's start at the beginning. After all, it's a very good place to start. So, for x between -1 and 1, find the Taylor series for f of x is 1 over 1 plus x squared, centered at x equals 0. Now, there's 2 approaches. One approach is take derivatives and hope for patterns. That's a dangerous approach. A better approach is to say, let's rummage through things that we know. And in particular, we say, does this look like anything that we know? Well, it does remind me of something. It reminds me of the following. We have that 1 over 1 minus something is the sum, 0 to infinity, of something to the k. And that's true for whatever you put in the box. So there's the question, what's in the box? What's in the box? Well, I should say it's almost true, right? And this is for -1 less than what's in the box, less than +1. All right. So you're probably thinking, that's kind of a clue, right? It was kind of a clue to think about geometric. And so we say, okay, well, can we think of 1 over 1 plus x squared in this way? Yes. We can say, look, 1 over 1 plus x squared is 1 over 1 minus x squared. So what's our box? Minus x squared. So this is the sum, k equals 0 to infinity, of minus x squared to the power k, which is the sum, k equals 0 to infinity, of minus 1 to the k, x to the 2k. Now, you might say, okay, wait, how do we know this is the Taylor series? Good question. How do we know it holds for the interval we want? Well, first off, let's do the second question first. If you plug in here, you need negative x squared to go from -1 to +1. The only way that can happen is if x is between -1 and +1. Okay, so that's no big surprise. The more interesting thing is, how do we know this is the Taylor series? Because we didn't do any derivatives. No derivatives were harmed in getting this answer. So is it right? It is. So here's the fun thing. If you find a series for the function, that's it. That has to be the Taylor series. So if you don't want to, and I would strongly recommend, you should not try to derive Taylor series from first principles. You should say, I've got a handful of things I know. Let me use what I know. Using things you know is great. Really, really, really useful. I always strongly encourage that. All right, part B. Find the sum of the series, -1 to the n, x to the 2n plus 1 over 2n plus 1, if you're between -1 and +1. And your answer should be an expression involving the variable x. Okay, cool. Now, let's compare. How do these look? Well, they chose to use n where I put k, but okay, all right. Fine. So, we'll do that. 1 over 1 plus x squared we'll switch to n, 0 to infinity, -1 to the n, x to the 2n. So, but again, take a look. Term-wise, how do you make an x to the 2n look like x to the 2n plus 1 over 2n plus 1? What do? You integrate. Okay, so that's what we're going to do. We're going to integrate. All right. Well, so we integrate everything dx. All right, well, here, integral of 1 over 1 plus x squared dx, arctangent of x. Now, when we do series, the series, we can do it term by term for where it's absolutely convergent. So in other words, from -1 to 1. So we push the integral through to get the sum. N equals 0 to infinity, -1 to the n, integral x to 2n dx, which becomes the sum n equals 0 to infinity, -1 to the n, x to 2n plus 1 over 2n plus 1. Now at this point you're like, cool, we're done. But they're going to check for something. They're going to check to see if you checked. So we're going to check their checking. What are they checking for? Did we put in a plus c? Because we need to check. So how do you find c? Well, you plug in x equals 0. And what do we get? Arctangent of 0. In the sum, you always have 0 to a positive. So that turns out to be 0 plus c. So, but arctangent of 0 is 0. So this says that c equals 0. Good. So finally, we get that the sum n equals 0 to infinity, negative 1 to the n, x to 2n plus 1 over 2n plus 1 is equal to arctangent. Arctangent of x. All right. There we go. Cool. You have some other questions perhaps. Why do we include these endpoints where before we did not? Well, if you plug in 1 or negative 1, you get something which diverges. It's the sum of negative 1 to the k. Basic divergence test. But if you plug in 1 or negative 1 here, what's going to happen? Well, you're going to end up with 1 or negative 1 upstairs, so it doesn't matter. 2n plus 1 downstairs and an alternating sign. So it's alternating going to 0. So it's convergent at your ends. It turns out, fun fact, we don't need to know this, but it's good to know things, that if we can say, look, we know how it behaves open interval, we find the antiderivative, and it converges closed interval, then what we think should happen at the endpoints is what happens. All right, cool. All right, so, cool. Part C. Find the sum of the series, negative 1 to the n, 2n, x to 2n minus 1. Okay, well, how do we get from where we started to 2n? See, here, we integrated. What do you do here? Differentiate. It's almost easier. I'm kind of surprised they didn't switch the order. So, we have 1 over 1 plus x squared equals the sum. Okay, well, we're doing n. N equals 0 to infinity, minus 1 to the n, x to the 2n. Take the derivative of both sides. Well, we take the derivative here. This one we have to think a little bit about. So this is like 1 plus x squared to the minus 1 power. So this becomes minus 1 plus x squared to the minus 2 times the derivative of the inside, which is 2x. Or that becomes minus 2x over 1 plus x squared squared. Okay, so that's the derivative of 1 over 1 plus x squared. Now, equals, and we do the same thing that we did before, term by term. And what are we going to get? The sum, n equals 0 to infinity of negative 1 to the n. Derivative here is 2n, x, 2n minus 1. Power comes down. Now, at this point, we're done. But you might say, Steve, that's 1. You put 0. Okay, true. But notice, what happens when you plug in n equals 0? You get 0 automatically. So you say, oh, okay. So we'll just shift and start at 1. So the punchline for this problem, or the way this problem flows, if you will, to find a Taylor series related to its geometric, recognize doing integration or derivative. And when we do integration or derivative of power series, term by term, piece by piece. All right. Well, we're at the end of our going through this exam. And you might be getting ready for your own final exam. I hope you do well. I know Calculus 2 is not the funnest class. I know it's challenging. Let's get done. Let's get through it and go on to bigger, better, funner things. I believe in you. Study, practice, review, work together, find friends. If you need to go yell on a pillow for a while, it's okay. There's a lot of pillows around. But be your best self. Get through this test. All right. Thanks for joining. Bye.